In this lecture, we are going to discuss dynamic error coefficients, but before moving forward, first let us see what are the disadvantages of static error coefficients because of which there was a need to introduce dynamic error coefficients. First of all, the static error coefficients are defined for only three standard inputs, which are step input, ramp input, and parabolic type input. These are also not applicable for unstable systems. On the other hand, dynamic error coefficients are valid for stable as well as unstable systems. When we try to find the steady state error by using static error coefficients, most of the times the error comes inaccurate. Most of the times, the error comes out to be 0 or infinity. Static error coefficients does not represent how the error builds up over time. This is a major drawback of static error coefficient that it simply tells us the final error value when time tends to infinity, which is steady state error. Otherwise, it does not show or represent how the error builds up over time. For non-unity feedback systems, the analysis for finding the static error coefficient is quite lengthy. First, we have to convert non-unity feedback system into unity feedback system, then only we can find static error coefficients, which is quite a tedious job. These challenges were solved by using dynamic error coefficients. Since dynamic error coefficients are defined for a general system, there is no need to consider unity feedback systems in particular. We can take a general system having feedback function Hs. For this block diagram, we will be having error function equal to Laplace transform of input signal R divided by 1 plus Laplace transform of feedforward function Gs multiplied by Laplace transform of feedback function Hs. Let us define another function Fs equal to error function Es divided by input signal Laplace transform Rs. Let this be equation 1. In mathematics, you might have studied Taylor series, which we are going to use here. The general expression for Taylor series is shown on the screen. We will be using the same Taylor series for expanding the error function Fs. Here, f-a, f"a are all derivatives of the function Fs. Like f-a represents one time derivative of the function Fs, similarly f"a represents two times derivative of the function Fs, and so on. Now, here is a very important assumption. Rather than finding and calculating different derivatives and their values, we have simply assumed that this expression will come out in the form of k0 plus k1s plus k2s square, and the sequence will go on. There is no need to calculate different derivatives, as our intention is to make this analysis easier, not to make it more complicated. That's why we have written this expression in another form without even calculating. Let this be the second equation. Here, the different coefficients of S, which are k0, k1, k2, k3 and so on, are referred as dynamic error coefficients. I hope all the steps until now are clear to you. Now, we will take limit on both sides of the equation 2, giving us dynamic error coefficient k0 in the left hand side to be equal to limiting value of the function fs, which is also equal to 1 divided by 1 plus gs multiplied by hs. That's how we can calculate the value of dynamic error coefficient k0. Now, let us differentiate the equation 2 with respect to Laplace variable s, which will eliminate the dynamic error coefficient k0 from the left hand side of the equation, and afterwards we will again apply the limiting value on this equation. By doing so, we will get the value of dynamic error coefficient k1 to be equal to limiting value of the derivative of the function fs, which is equal to 1 upon 1 plus gs into hs. By following the same procedure, we can find the value of different dynamic error coefficient. In general, the value of nth dynamic error coefficient is equal to 1 upon n factorial multiplied by the limiting value when s tends to 0 of the expression nth time derivative of the function fs with respect to Laplace variable s. That's how we can calculate the different dynamic error coefficient. We can also write error function in terms of dynamic error coefficient. From these two equations, we can also write error step function is equal to k0 multiplied by rs plus k1 s into rs and so on. Taking inverse Laplace transform, we will get generalized error series. In this expression, the error is represented in terms of dynamic error coefficients and different order derivatives of input signal R. When we were talking about static error coefficient, we already took unity feedback system, but when we were discussing dynamic error coefficient, then we had taken a general system in consideration. Now assuming if we consider unity feedback system in both the cases, then we will have this relationship between dynamic and static error coefficient. The dynamic error coefficient K0 will be equal to 1 upon 1 plus positional error coefficient. Dynamic error coefficient K1 will be equal to 1 upon static velocity error coefficient. Similarly, dynamic error coefficient K2 is equal to 1 upon static acceleration error coefficient. One thing you might have seen and will be seeing in future lectures also, that most of the times I consider negative feedback system. But what if in the exam the question is of positive feedback system, then what will you do? Many times students get panicked for no reasons at all. Even if a positive feedback system comes, then simply introduce two negative signs. One sign at the comparator and the other sign at the feedback function. Because if you multiply two negative signs, it will eventually give us positive sign. And the positive sign is converted into two negative signs so that our system again becomes negative feedback system. The only thing now you have to keep in mind is that wherever you have put the value of feedback function hs, then at all those positions you have to introduce a negative sign also. For example, the dynamic error coefficient k0 will now be equal to limiting value when s tends to 0 of the expression 1 upon 1 minus gs dot hs. This negative sign came just because of the function hs, because in every expression wherever hs is present, we have to replace it with negative of hs. That's why here the negative sign came. Steady state error is very important topic. Many questions are framed from it. But if you study little bit deeper, then you will find the topic static error coefficient, and few questions may come from this in competitive exams. But if you dig more deeper, then you are going to find dynamic error coefficient, which is actually not present in many textbooks which are meant for undergraduate levels. Also, questions from this topic rarely comes in competitive exams. You can actually dig more deeper if you are interested in this topic. However, it will be much better if you first complete the syllabus, then afterwards you can do research on any topic you wish.